I am Dr. Muhammad Shoaib, and today we are going to study Introduction to Photochemistry. In this lecture, we will see basics of photochemistry, such as principles of photochemistry, difference between thermal and photochemical reactions, laws of photochemistry, and quantum yield. First of all, what is photochemistry? As the name shows, photo means light, and the study of chemical reactions taking place in the presence of ultraviolet and visible light. This study is called as photochemistry, and such type of reactions are called as photochemical reactions. Wavelength of this light is 200 to 800 nanometer, and we know that the energy of photon light is in the form of photons, and the energy is quantized. Photochemistry is very valuable in organic and inorganic chemistry, and it proceeds differently than the thermal reactions. Many thermal reactions have their photochemical counterparts, mean that there are some reactions which takes place thermally as well as photochemically. There are certain advantages of photochemical reactions, such as it forms thermodynamically disfavored products. That is, those products can be formed which are not stable, which are not possible by ordinary thermal reactions. By using light, a large activation energy barrier can be overcome, and the photochemistry is very vital in the nature. It is the basis of photosynthesis, vision, color perception, and formation of vitamin D. However, sometimes it can be destructive, as in the degradation of plastics. What is electromagnetic spectrum and visible light? The term radiation include electromagnetic spectra and even the beams of electrons, protons, and neutrons, etc. Here is the electromagnetic spectrum, which includes gamma rays, X-rays, ultraviolet rays, visible rays, infrared and microwaves, and radio wave. All these radiations have different uses, but photochemistry deals only with this region, that is called as visible, and the some region of ultraviolet. These radiations are very widely used in chemistry, such as the spectroscopy is completely based upon the electromagnetic spectrum, and the visible light deals with the UV visible spectroscopy. But here we will study the chemical reactions taking place in the presence of light. All the radiations incident on matter are not involved in chemical reaction. Some of it is transmitted, some is reflected, scattered, or refracted. Only the fraction of absorbed radiation is used to produce chemical reactions. Here is a definition. A reaction which takes place by absorption of visible and ultraviolet radiation is called as photochemical reaction. For example, hydrogen and chlorine do not react with each other when there is no light, but in the presence of light, H nu, hydrogen and chlorine reacts to form HCl, that is hydrochloric acid. Here is the famous HCl Cannon experiment. If we fill a tube with equimolar volume of H2 and Cl2 and a handball is placed on one side, when the lamp is switched on, hydrogen and chlorine will react to form HCl gas and it will behave like a cannon. Similarly, those reactions which are caused by heat and in the absence of light are called as thermal or dark reactions. That is, no light is a requirement for such reactions. These reactions can take place in the presence of light, but the light is not the primary or key requirement for such type of reactions. Here are the principles of photochemistry, which are: the activation energy is provided by the light. This light does not only activate the molecule by changing its activation energy, but it can also change the symmetry of molecules' electronic configuration. And the photochemical reactions are sometimes very fast. They are completed in 1 nanosecond, that is 10 raised to minus 9 second. And some of the process associated with these chemical reactions are completed in 10 raised to power minus 15 seconds. The photons of light are absorbed directly by the molecules or in the presence of some photosensitizers. For example, in the process of photosynthesis, chlorophyll is not a reactant, nor it is a catalyst, nor it is a product, but it is a photosensitizer. It absorbs light and transfer it to the molecule of reactants. And sometimes photoexcited state is deactivated by some other chemical reagent, and it is the reverse of photochemical reaction. It is called as quenching. Here are some differences between photochemical and thermal reactions. First is that photochemical reactions taking place in the presence of light, while the thermal reactions do not require light and they involve the absorption or evolution of energy in the form of heat. Second is the presence of light is primary requirement, while for the thermal reactions light is not the key requirement. Third is in photochemical reactions temperature do not have a lot of effect, while in thermal reaction temperature plays a significant role. Fourth one is delta G, that is Gibbs free energy for photochemical reaction is positive, while the Gibbs free energy for thermochemical reaction is always negative for spontaneous reactions. Fifth is photochemical activation or photochemical reactions are highly selective. That is, some of the reactions can take place in the presence of light, but they will never proceed in the absence of light. The thermal reactions are not very selective. Here is a famous example of chlorophyll formation, and here is the glucose formation, and here is the examples of carbon dioxide, ammonia, or thermal decomposition reactions. There are many types of such reactions. Next are laws of photochemistry. There are two laws. First law of photochemistry are Grotthus-Draper law. This law is very simple and self-evident. It states that only the fraction of incident light is absorbed and bring about a chemical change. That is, the other fractions of light which are reflected or transmitted do not produce any chemical change. Next is very important. The absorption of radiation or light must not necessarily be followed by a chemical reaction. That is, it is not necessary that if a molecule absorbs light and it will be converted into product. In many unfavorable conditions, the absorbed light remain unused. Sometimes it excited the molecule, but the molecule is de-excited, and sometimes the absorbed light is re-emitted as heat or light. There is a disadvantage that this law is purely qualitative in nature, and it does not provide any idea between the relationship between absorbed radiations and the molecules undergoing photochemical reactions. Next is the second law of photochemistry, which is called as law of photochemical equivalence or Stark-Einstein law. It is also very simple, but it provides quantitative relationship between the absorbed light and the molecules taking part in chemical reaction. It states that each molecule or atom of the reactant absorbs only one quantum of light and activates it. Simply one quantum per one molecule. In other words, each quantum of light absorbed by a molecule activates only one molecule in the primary step of photochemical process. Here is a molecule. When it absorbs one photon, it is activated or excited. But it does not mean that one molecule will react by absorbing one quantum of light. But it states that only one molecule is activated by each quantum of radiation or photon of light. Here is a pictorial diagram, and if there is a 1 mole of reactant molecules, then the energy will be equal to the 1 mole of photons. Photoexcitation. When molecules or atoms absorb light, they are excited to higher electronic or vibrational or rotational energy level. Basically, there are electronic energy level. Each electronic energy level has many vibrational energy levels, and a vibrational energy level has many other rotational energy levels. And each excited state has a definite energy, lifetime, and structure. The excited molecules or excited species are highly unstable, and their lifetime is usually 10 raised to minus 8 seconds. Once excited, it decays at once. Sometime it decays back into the reactant and sometime into the products. We will see here is a decay of photoexcited molecule. There are two types of decay. Here is excited species. It can be of molecule or an atom. One type of decay is non-reactive. That is, it does not involve any chemical reaction. It is further divided into two types. The absorbed light can be re-emitted in the form of fluorescence and phosphorescence, or the decay involves radiation-less transition, that is internal conversion or intersystem crossing. We will study in our next lecture the Jablonski diagram, which involves the upper half, non-reactive decay. Or this decay can be reactive, that is, a reactant molecule which is excited can be converted into product, or it can transfer its energy to some other molecule which is converted into product. Here are primary and secondary reactions, or we can say primary or secondary process. The overall photochemical reactions consist of primary reactions and the secondary reactions. Primary reactions are the immediate consequences when light is absorbed by some molecule or an atom. And after primary reaction, the subsequent chemical changes are called as secondary reactions. Here are some of the primary photochemical reaction or processes. We will see in our next few lectures the secondary reaction, which involves the chemistry of olefin, Norwich type 1 reaction, Norwich type 2 reactions, and there are hundreds of such examples. Here is a molecule ABC which absorbs light. It can be dissociated into radicals or into ions, or it can involve photoionization, or the light absorbed by the molecule bring excitation in that molecule, that is called as photoexcitation, or the molecule is rearranged by absorption of light. Next is quantum yield. The efficiency of photochemical reactions or processes is often expressed in terms of quantum yield. Quantum yield is shown by the Greek small case letter phi. Conventionally, it was shown as small case letter phi, but now the uppercase letter phi can also be used. Below, the reference of a paper of Royal Society of Chemistry is given for the reference. It states that the number of molecules reacting per quantum of light absorbed, that is, per quantum of light, the number of molecules which are converted into products is called as quantum yield. The energy absorbed per mole of the reacting substance is called as 1 Einstein. Usually, we do not take reactant as molecules, we take our reactants in the form of moles. So 1 mole of photons is called as Einstein. Energy of 1 moles of photon is called as 1 Einstein. Or we can say that the quantum yield, it is a ratio between number of moles of reactant consumed per Einstein absorbed. Quantum yield can be very high, low, or it can be equal to 1. Here is an example of high quantum yield, that is, one chlorine absorbs one photon and the primary process takes place. Then the free radical reaction starts and a chain reaction starts. Quantum yield is 10 raised to power 4 to 10 raised to power 6, that is 10 raised to power 4 to 10 raised to power 6 molecules are converted by absorbing only one photon. Sometimes quantum yield is low. The reaction of H2 and Br2, it has a quantum yield of 0.01. The reason is that sometimes excited molecules are de-excited. They lose their energy. Sometimes the intermediates formed as bromine here or hydrogen here are converted back into the reactants. In last two process, we can see that the H2 and Br2 are formed, which are the reactant molecules. Therefore, quantum or photons are absorbed, but molecules are not converted into products. There can be three possibilities. If quantum yield is greater than 1, it shows that there is a chain reaction or free radical reaction. If it is equal to 1, it shows that the product is immediately formed in primary photochemical process, and if it is less than 1, then the physical deactivation is the dominant phenomena. Here is one example of the synthesis of glucose by photosynthesis. One molecule of glucose is synthesized when 48 light quanta are absorbed. And that's all about basics of photochemistry. Next, we will study the photophysical process in the lecture of Jablonski diagram, and photochemical process. We have several lectures. I hope that you got these points, and thank you for watching.